Carry on.
I'm not used to holding this thing. Okay, so now you have an understanding about, because we take a poll before the starting and there were 3 challenges. One, the programming among all of us. Second was SIR compartmental type model, and third was estimating parameters, right? So you have seen 2 of those things.
You said we could do another session on estimating.
Okay.
So you could do R0.
Okay. Okay, so well, why are we doing these things all? The importance of here, and how I'm changing the slides.
Slide changer.
Oh, thank you. So the important thing here is, well, you know, you estimate these parameters, and then what? The question is, what do we do? What is the bigger picture there? You use these estimates to do something else which is useful from a disease outbreak perspective. So one of the things which are very critical to know about is the intensity of an outbreak. And you see in modeling of disease models papers, if you see the literature, 50% of the paper is on intensity of the spread, 50% of the paper. And in technical words, we call that thing as a reproduction number. How many of you have heard of that? Reproduction number. Have you all seen the SIR model or no? Not? Kind of. Okay. So, so basically what Padu was mentioning about SIR type model, and we also referred in our talks, it's 3 buckets: susceptible buckets, infected buckets, and recovered buckets. And they are attached to these tap, you know, water tap, and they are attached to each one of these buckets, right? And these rates of tap are different, right? And so you open these taps and the level of this will fluctuate as the time will progress. And that is what all is about SIR type model. And he mentioned few details in it, like having exposed class, having vector-borne aspect. You can make it very, very complex, those models. So this is just a brief outline of it. So let me go back and show you some of the things that, that are critical in that. For example, this is an SIR type model where there is this tap is leaking out this S compartment, and this compartment is getting added by this tap, and this is getting leaked by this tap. And then this is a third compartment where this tap is actually adding into that. You know, so it is, these rates are changing over time because these are multiple of these state variables as well. So what happens, there is a quantity which is formed as ratio. Think of this. If this is a bucket and it has a tap which is filling in and a tap which is leaking out, what will happen to the level of it? It depends on how this ratio of these parameters are changing, right? And that's how we'll tell what is the level of this bucket over time. So that we refer it as R0, or basic reproduction number. And this is a very important quantity. Why? Because, and as I said, 50% of the paper in modeling literature is talking about, in some sense, about reproduction number. And the reason for it is in the next slide, you will see it. But before that, if you simulate that thing the way Padu was mentioning, if you simulate these models using this numerical scheme, you will get an outbreak. If R0 is bigger than 1, there is a disease. If this number, this ratio is less than 1, that means what less than means 1 means that you are filling in less quantity than you are leaking it out, right? So there will not be an outbreak, the disease will quickly die out. And this is the number of infected people, that means I bucket. Is that okay? People who have not seen this SIR model, my question is to them. Okay, so this is very, very straightforward, very simple. I want to keep track of number of infected people over time, and this depends on this quantity, this ratio, how much it is filled in and how much it is leaked out, and whether you will have a peak or whether you will not have a peak. Not only that, but it also tells you whether the peak will be high, low, or it will be more smoother curve. So for example, if R0 is, as you increase the value of R0, the epidemic quickly occurs and goes to a very high peak and drops down very quickly. Okay. And this is in a natural life, you see it in outbreaks, which are single outbreak. Single outbreak means one which dies out. There are many diseases which doesn't die out. For example, HIV outbreak, it is still going on, right? Malaria is endemic in many parts of the world. So those are different diseases. This is not what a disease. This is like flu. Every year there is a flu outbreak and this dies out. There are many diseases like that. Okay. Ebola was like that, single outbreak, right? Zika was also single outbreak. So what today we will be doing, okay, before we go further, you know, this thing, people have done very hard work to estimate this reproduction number R0, and this is what we will learn today. How we will get a handle of, if given a data set, first of all, what data set is needed, and if that data set is available, how do you estimate R0, right? And this is very critical, as you can see in this table. Even for the same disease, these are different diseases, these are their reproduction numbers. Depending on the year that you are using, you could have different reproduction number, but roughly the same. What it is telling you, how fast the disease is spreading in the population. Okay. For example, which one is the having a highest? Okay. Measles are the one basically has the highest reproduction number. It's not listed here, by the way, but measles. Have you all heard of measles? It has a very high, like around 19 and 20, which is a very high reproduction number estimated from the real data. So these are different outbreaks from different diseases. They have estimated it. So in fact, there are researchers who have put their whole life in estimating these reproduction number for the diseases to come. It's very important quantity, and this is something that we have difficulty. This is the only, you know, how many of you have seen an English movie called as Contagion? Have you heard of a movie Contagion? It's a very good movie. You should see that one. You know, these movie directors do lots of research to build these movies. You know, they don't know about these disease modeling, but they are using these terminology in that movie, and they have done lots of good research behind the scene. Probably they have not cited that yellow book of Carlos. They should have cited it in that book, in that movie. But that's a very good movie, you guys, if you get a chance. It's a Contagion, it's on disease outbreak. And who's there in that? Kate Winslet, I think. Kate Winslet is there in that. And she's an epidemiologist who is explaining reproduction number and the disease intensity. And you know, we don't take it that seriously, that reproduction number, until you see that movie. If you see that movie, your way of looking at the modeling will change. She has explained so well, even though she has no idea about reproduction number before that movie. Probably after that movie, she would have learned that thing. So this is something, that background I want to give you about. 1918, there was a swine flu outbreak which killed 15 million people. 1918, it was a major outbreak of flu, and its R0 was 1.4 and 2.8, roughly around that. Okay, so there are multiple methods. Actually, these numberings are all messed up, but there are multiple methods for estimating R0. Well, one is by fitting to the incidence data. Second is by sampling methods. Next one is exponential rise of the curve, and then the other one is the final size expression. So we don't have that much of time to go over all these methods, but I will give you very brief outline on 3 methods very easily, and very, very simple to apply it. Very simple. And you can do a cutting edge work if provided you have a data for the outbreak, any outbreak that you are talking about, single outbreak. Okay, so so this method is what Padu was mentioning about, incidence method, which involves optimization, and we would not do it here because it requires much more skill set in that, and we don't have that much of time, and I think we might have another session. another session, that's the time we can do it. But I will talk about the remaining 3 of the methods very quickly, and it will also provide you with the R code. Very simple, you will see. Do you all know regression, right? Line. Regression means a line, a straight line. That is all we need. Okay. So the first method is a sampling method. In sampling method, you are assuming that all the parameters are known to you, parameters of the model, beta, gamma, whatever the parameters are, and they are going in the reproduction number. So for example, there was a model of the R0 looks like this. This is a different model, and the parameters beta, nu, mu, and alpha, the distribution of those are given from some field study. See, something you have to be given, otherwise you cannot find other thing. So this is known to you somehow, and you sample using something called as Latin hypercube sampling, and then you generate so suppose you pick, in order to compute one value of R0, you need one value of beta, one value of nu, one value of mu, and one value of alpha to generate one value of R0, right? So if I randomly sample from here one value, randomly from there, and so on and so forth, I will get a randomly generated R0 value, right? Because I have not done any bias to the sampling. You know what is sampling means? I close my hand and I take the, but I have to be careful that I have to sample such that this shape is maintained of the probability. How many of you have done probability and statistics? Okay, so everyone has seen some of these. Okay, good. So this is one way of doing, very easy way, but for that most of the time you have to know the distribution of it. Very simple method. And in the as Mugdha was mentioning, and Padu also mentioned a code here, the only thing you have to do is R uniform. You have to sample R uniform in the R code, and you can generate one samples of each one, and you get a distribution of reproduction number. This is called as a sampling method. Now there are sophisticated method of sampling. Well, we don't want to go, every method has its own sophistication. People work on these methods for their whole life, so they have different variation of these methods. I'm just talking briefly on this thing so that you get to know how people do the real life research. Now the second method, third method, sorry, is the sampling method I talked about when the distribution of model parameters are known. Next method is exponential rise of the curve. Now what happens when there is an outbreak which is starting right now? That outbreak usually is a naive outbreak. What that means is people are not really serious about it, and serious is because they are not really truly aware of the intensity of it, and there are not any intervention applied for it. And that is what, in that circumstances, the outbreak is spread like exponential curve, and that's why we call it as exponential. Early stage is always an exponential rise of the curve. We can't use the later stage data for it. We only used an initial stage of data. And you can see that every curve start exponentially of any outbreak, and then it started to turn downwards. And so you cannot take a data after a certain time period, and you have to test that, how many data points you should take in this thing. So, well, so everyone knows this model, right? This is a linear differential equation. You solve it and you get an exponential curve, right? So, and this is what we are saying. So if we have some model like this, then we know it is an exponential growth rate, right? Now remember, the Padu was mentioning about SIR model, right? In this model, is it linear or non-linear? It's a non-linear because this is a quadratic term here. But you can linearize it. You can linearize around certain steady states of like 0, 0 state. As soon as you linearize it, you get something similar like that. The only difference is there's a matrix here, which is a square matrix of, in this case, because the population is constant, you just need 2 equation here, right? So it will be 2 by 2 or 3 by 3. right? 3 by 3. Everyone okay with that? Now think of that. What is this parameter here? Is this parameter in this case? What will happen in this 3 by 3 matrix? What will be this parameter? This is an important parameter, K. Why? Because this tells you how fast the exponential growth is happening. Growth rates. But in the matrix, what is that growth rate? Think of that. In the matrix, what is that growth rate? Well, it is described by the eigenvalues, right? Eigenvalues are the ones which describes in which direction the curve will going to have the faster growth rate or lesser faster. There are 3 dimensions here, right? Because this is the 3 equations, 3 dimensions. Everyone okay with that? Yes, no? Everyone has done linear algebra, eigenvalues, right? So the largest eigenvalue is what describes the exponential growth rate. Everyone okay with this? So if you can estimate that largest eigenvalue, you are done, right? You are done if you know the largest eigenvalue of the system. You know, and now I will show you how you will estimate the R naught if you know that largest eigenvalue. Spectral radius, right. So what we do is, so we linearize the system. This is a linearization of system, and you find the characterization of the matrix, right? And so what we do is we separate all the we take the largest eigenvalue by some basic ideas of whether, well, you will see it in these type of model. It is very straightforward to find out you can compare the eigenvalues basically. So it turns out this is when you find the characteristic polynomial, I substituted this row here is basically your K here, the largest eigenvalue. The row is largest eigenvalue, which is coming from this expression. You know, this is a characteristic polynomial, right? And then what I do is, think of that, forget about this part here. This much part is coming from a characteristic polynomial. The only thing what I have done is, instead of lambda here, I substituted rho, which describes the largest eigenvalue. Is that okay? Think of this part, right? Now I look at my R naught for that model. In this case, the R naught for the model is this, right? And I isolate all the betas. The betas usually comes in pairs. In this model, it is simple to do that. And you isolate betas in terms of R naught and rest of the parameters. So you get, see, beta is gone here. Can you see that? Everyone okay with this? Yeah? So now, forget about this thing. We have an equation which describes what? R naught and the largest eigenvalue. Is that okay? R naught, I have an equation which is a R naught and a largest eigenvalue. Everyone okay with this? Okay. Next, how do I find this thing? So if I know rho, rest of the parameter I am assuming that I know. Rest of the model parameters I am assuming I know. The only thing I don't know, what is the largest eigenvalue? Sorry, the exponential growth rate. If I know these row here, I can estimate R naught from this expression. Is that okay? Okay. So this is the R naught expression with rho here. So the only thing is R rho. Now think of that. I can use a simple this exponential curve which Padu has written there, which is like this, right? And rho is, and fit this exponential curve to the real data, using a real points, and estimate this thing. Now there are more simple things that you can do it. Look at this thing. If I take a log, I convert it into a linear line. I convert into line. Can you see that? It's a line here. Line in terms of log yt and rho. Rho is a variable here. Is that okay? So then what we have to do is we have to use the data in a log form over time. The data is what? What is the data? over time you have number of cases that have been reported, right? And you will not be able to take, if I use this equation, then I will not take the y value, instead I will take a log of y values, right? So if I do that thing and I fit this straight line, I can obtain what is the estimate of a rho using Excel, using any type of simple software. Is that okay? Yes or no? Okay. So once you get this row, you are done. You are done because you can substitute rho here and you can estimate R naught from here. Okay. Now I have kept my slides there. You are free to use it and see around it, and I can provide you some references also. Now if you use MATLAB, in order to do that you need regress. Is the function is the MATLAB. In the R is, now why do we use R? I'll come into a few minutes in that. You used LM. LM is used as an inbuilt function for doing regression. And this is the way you have to do. YLG is this quantity, and on time, different time points is what you use to do the regression in that. Okay. Now, why do we use R, by the way? Why do you want to use R? You know which is the most popular language right now? Right now R has taken even some of the very, very famous statistical software, including SAS, S+, all these things are now lagging behind, and R has taken a forefront on these things. It is free, that is the most important thing, plus it is cross-platform. That means I can use it along with other softwares very easily, or vice versa. I can use other software inside R, which is a very, very compatibility issue. There's lots of, because everyone wants to sell their product and they don't want to make it compatible. But R, that is not the case. And since it is a freely available, there are everyone is generating their own packages in their own area. So it is very good software in terms of using it. Okay, so the next one, I'll go to the third one, and I do have 5 minutes, and I think I've promised to cover in the 5 minutes. So using final size expression, and what is final size means? What is final size means? Has anyone heard of final size?
What happens at the increase?
And well, that is, yes. So final size literally means how many people total got infected in a one outbreak, right? Okay. Yeah, from our mathematical sense, that is what we mean by saying S infinity or R infinity.
One quick question. But in all this, what you are doing, R naught, what you are calculating is also effectively for the linear system only.
Sure. Sure.
Actually, because how true is it when you are calculating R naught? Because we are actually speaking about linear system only. But the nature is actually totally non-linear.
Well, that is what I said. In the initial stage, the nonlinearities that are occurring are less effective, and outbreak are growing freely without any outside impact of human interventions or anything like that. Plus, you are absolutely correct. There are, again, these are all approximate methods. These are not regress methods. These are not mathematical methods. There are a lot of pros and cons to all these things. But you know, if we cannot do mathematically, that doesn't mean we should not take a step forward, right? We should always have, I mean, in mathematics, we always do in numerical methods. It's all about approximation. Taylor series is all about approximation. 50–60% of the mathematics is about approximation, right? So everywhere we do it. Here also we are doing. But you know, the data linking is a very challenging task, and sometimes the outbreak data is less known, or it is hidden, or it is corrupt, and we have to deal something like. So I teach a course which is called as uncertainty analysis or uncertainty quantification. Well, we don't have a time here, but let me see. I will cover probably with the Padu in the next, if there is time. So third one is about, again, this model. Now, this model was for
what was just said. So that's an approximation can be improved if you go for different varieties of linearization. What you're talking is a base level utilization.
Right, right,
So
right.
improved levels of utilization can be done.
Sure, that's a good point. That's good.
Still, there is some
Yeah,
amount of-
this.
So there is a step forward.
Yes, yes, yes. Yeah.
Good area for research.
But that is,
Even for example, if you want to make a little more reliability, anyhow, you're not going to get 100%. A little more increase, just raise the level.
well, that's a good. So this is a more like a discussion. So please do share your ideas on these things if you have more ideas on any of these topics. Yeah. Okay, so this is a SIR model for directly transmitted diseases, but we also discussed about vector-borne diseases. In this, the vector population is also added onto it, and they are impacting each other. Now, one approximation could be to assume, think of that. Now, we have to always think of biology in this case. You know, human population, what is the lifespan of human on an average in India, for example? 60 years? 60 years? What is the lifespan of the mosquitoes? 14, 15 days, adult female mosquitoes, because those are the responsible for the transmission. Well, as compared to those two, well, think of the time scale is very fast for the vectors as compared to human. So you can make some biological assumptions here and say that you have reached a steady state in a vector population, quasi-stationary state that people call it in the literature. And then you get something like that, you set it equal to 0 right hand side, and you get this IV, and then you substitute IV into the host equation. These are the three host equations. H stands for host and V stands for vector. So then from this equation you can find IV. By the way, this is a fraction there, and then you substitute in this thing IV, and you make few more. So when you substitute IV in this equation, you have to combine all these values, because SV is now a quasi-steady state, and IV is also you are taking this system under those assumptions that that a vector population is evolving very fast. You can assume that thing, and so you have now a smaller system which is similar to that. The only thing you have lost here is the meaning of the beta. Now this beta, new beta, has no meaning, no biological meaning, but mathematically it is more tractable now. So there is a compensation everywhere. Everywhere you do any approximation or anything like that, you will lose some kind of things. And so this is so now this is there, and R0 is again the same way. So you can do some kind of division, which you will find it in the yellow book that you have today. And if you divide IH by SH, you can actually get an equation like this. If you divide IH equation by this one, and you can actually solve this equation. And so you get some, after integrating, you get equation like this. And you can take then the limit and you get something like SH infinity. SH infinity is what we call it as a final epidemic size, once you take a limit t goes to infinity. So, and it turns out when you do these integration, the R0 beta over gamma H is coming very systematically here. And you can write down R0 instead of beta over gamma H, you can write down R0. Now you can isolate R0, and in fact, so let's see how you got this thing. So note one thing, either you get S infinity or you get R infinity, which means at the end of the outbreak, how many susceptible are left, or how many R are there, is one and same thing. Why? Because there is no birth, there is nothing coming in, and there is nothing going out. If there is no infection, this will not occur, right? So whatever, you start with certain number of susceptible, and after an outbreak, it will remain constant, it will not change, right? So that is an S infinity. Some people also call that as an final epidemic size, because that is a size you have reduced. Sorry, S0 minus whatever S infinity is what the size you have reduced. Is that okay? And same thing here, whatever the value of the R final is your final epidemic size. Is that okay? Okay, so this formula is used sometimes, actually you can write down like this. This formula is sometimes used to get R naught, estimation for R naught, approximation for R naught. Okay, so there are various methods to find this, well, one way to do is, there was a data on influenza outbreak that Padu was mentioning in the morning, outbreak resulted in 512 total infection. Now this is a beautiful data set. Why? Because this happens in a boarding school. So no one was coming in and no one was going out. Once they were there, right? And so total infection were 512. So we knew in this case final epidemic size. Sometimes this is known to you. In that case, you simply substitute those things and you can find out R0 using this estimation. Okay. So this is all I have for you guys. So thank you very much. I think, oh, this is the code I have for computing final epidemic size. And this is the, you look at this formula, 1 minus final size minus exponential of minus 4, and this is the same formula that you are having here, right here. Okay, so the same formula I'm using to do some kind of understanding about relationship between final epidemic size and R naught. So, okay, thank you very much.
We thank Professor Anuj and